CubeSats. Small, inexpensive, fully functional satellites that actually fly in space. How are students getting involved in this exciting program? How is NASA helping deploy these tiny technological experiments? Find out on NASA Edge.
Hey, here's the interview I did with Garrett on CubeSats.
Oh, the satellites, where you build your own satellites?
Yeah, the interview that you didn't come to.
Was that on the schedule?
It's been a couple months at least.
All right. Yeah, I'll
Well,
check.
I tell you what, check the schedule. We got Cal Poly in a couple days.
I'll be there. I'll be ready for Cal Poly. Trust me.
All right.
We'll get this right. This CubeSat. This is good.
All right. So Garrett, what made you want to get into this whole CubeSat business? I mean, you're launching some pretty expensive payloads down at Kennedy. I mean, why would you want to put some of these smaller CubeSats on with the primary payloads?
And as you know, NASA is very big on these STEM activities, our science, technologies, engineering, and mathematics.
Right.
And also is training our current workforce, our new workforce for the future. Since '07, there's several success stories of these students that have been working on these CubeSats, has gone into industry, working with new industry partners, or actually coming to NASA and is working for NASA now.
Now you call this program the Alana program?
Yeah, Educational Launch of Nanosatellite. And it got its name back in the beginning because the key is education. So you have the CubeSat Launch Initiative. That's where we make the selections.
Okay.
So the priority list comes to me. I pick the list up and I say, who can I go fly on? So I try to go find matches for these vehicles, and once I get a complement of payloads, we create the Alana missions. Right now we're at Alana 7 on our mission manifest list.
Now, how many of these CubeSats can you put on a launch vehicle at one time?
It all depends on which vehicle it is.
Okay.
On a Taurus XL, we were able to put one P-pod. Now, a P-pod can hold 3U of base or configuration. Now, that could be 3 1Us or 1 3U CubeSat size or configuration of those. On other vehicles, like an Atlas V, we can put 8 P-pods on that vehicle.
Oh, wow, okay.
On Delta IIs, we were able to put 3 P-pods. So this depends on which vehicle it is, the space allocated to us, and the amount of mass of performance left over from the primary.
For the students, I mean, they're getting experience in building a satellite from the operations side, but also they're learning new science. But from your side, what are you getting out of it?
Well, part of the project or the program is for the data that's collected from these spacecraft, NASA gets this information. So when we put one of these spacecraft up on orbit and it's studying space weather, NASA gets this data back, and we can identify it, we can analyze it and say, hey, this is some pretty good stuff. We want to take a bigger spacecraft and go do that region or not.
Nice.
Or we can take a look at new technologies, like we can fly a new processor chip, put it on orbit, see how fast it really does work on orbit, and then take that chip and then go put it in a big spacecraft.
If I'm a university and I want to test a piece of material in space, they have to go through all the protocols that is necessary for that piece of material to fly into space, though, right?
Yes.
Okay.
They have to meet the same requirements as the primary spacecraft.
Okay.
Actually, a little bit stricter, because we have to ensure that the CubeSat and the P-pod themselves, the carrier, will not cause any harm to the primary spacecraft or the launch vehicle itself.
So what's an example of a pretty exciting experiment that was done using a CubeSat?
RAX-2, it flew on an MPP mission, and it was able to detect some space weather activity for the first time measured from space.
Wow.
Now, we measure from the ground, but they've actually measured from space. Another one, CXBN, has a sensor on it that's measuring a energy region in space that NASA has never studied before. And these are, very small, first of their kind, and there are problems with these. You get up there, you experience problems. That's what the whole idea is. Right. You learn from these things, and so there's a CXBN2 probably going to come down the pike and says, hey, we're going to make it better testing. RAX-3, we expect to see that one day? Probably so. But what we're also seeing is that they're taking the technologies from these small guys, these 3Us, 1Us, and they're building bigger spacecraft, because now they got the technology demonstrated to go and put bigger sensors on, because now they know how they go measure those particular regions.
According to all the websites on the internet, it really is possible that I could build and fly my own satellite. When we head out to Cal Poly, Franklin and Chris can get some interviews, and I can do a little industrial research to help with my design. If I come up with a brilliant presentation, I could actually become a real player in the satellite community. We're here at Cal Poly at the CubeSat department talking about satellites. When you talk about satellites, it's exciting. But when you talk about the program that allows students and perhaps podcasters to build their own satellites, then you get really interested. Of course, I came up with some great ideas, and I thought what better thing to do than to talk to these students, get their input on making my own satellite. They were incredibly open-minded and helpful in sharing their designs. In fact, some of them actually dared me to use their designs. With some hard work and possibly some correspondence courses on engineering, I hope to make BlairSat a household name. Well, maybe not a household name, maybe an institutional name. Academic institution.
So Jordy, how did Cal Poly get in the CubeSat business?
There was a need for students to train in satellite development by building satellites. And at the time, they were building bigger spacecraft that took a long time to develop. They were very complicated and expensive. It would take longer to do the spacecraft project than the time the students spent in school. And we were trying to find a way for students to be involved in the entire life cycle of a project. So they would start with the design, build it, launch it, and operate it in space, hopefully within about 2 years. And one of the things we decided was a way to accomplish that was to go with smaller, less complex spacecraft that the students couldn't, if you want to say it that way, couldn't get themselves into so much trouble. So what we decided to do is to start with a PicoSat, which is a satellite that's less than 1 kilogram.
Okay.
And that made it small, simple. And then what we did is we said, well, we also need to make it easier to launch. So we need a way of convincing launch providers that we are a safe alternative or a safe proposition for their flights.
Right.
So what we decided to do is to put them inside a box. And that's where we designed the P-Pod.
So this is the P-Pod. This is your design?
Yes. We can open it and see that it's basically just a jack in the box. When it reaches space, the door flings open, and then there is a spring inside that pushes the satellites out.
Gotcha.
It's very simple, but it's a protective shell in case something goes wrong with the satellite. Because a lot of times people will say, well, it's a student spacecraft, you know, are they following the same quality requirements as the other spacecraft? So we added a layer of security for the launch provider. So that's kind of the idea and how it started. There was not a lot of funding.
Right.
There was not a lot of interest because there was very little you could do with this spacecraft. But for us, if you could build a Sputnik, that was enough, because the training is what we cared about.
So the idea is you're building a Sputnik inside of a P-Pod, and you can actually launch multiple Sputniks into space.
And then the other thing we did with the standard is a lot of universities could work together because everybody had the same problems. And initially, about a dozen universities around the world decided, yeah, this sounds interesting, we're gonna try to do it. That was the initial spark.
And the great thing about the CubeSat program is that sort of like the Getaway Special or the gas canisters back during the shuttle days, which I was a part of as a student, where when I graduated, the Getaway Special wasn't finished yet. Whereas with this CubeSat, actually it can go into an engineering program, design, work on this, and fly, hopefully by the time I graduate.
And we got a lot of lessons from the Getaway Special because it was another way of having this compartment with the payloads go inside, very protective of the shuttle, and then the students build their experiments inside. So in some ways, it's a similar concept. It's just that it's a free flyer and much smaller.
I understand when you first started out, you were working with international partners for launch, using launch vehicles?
Yes, initially it was difficult to get launches in the United States at reasonable prices, and we did our first few launches were in Russia. And it actually was a very valuable experience because it was the first time we put them in space, we proved the concept, we showed people that it could work, and very quickly people in the US decided this may be interested and started working on it. And in fact, NASA was one of the first US government developers. They lost the shuttle because of the accidents, and they needed to do some experiments, and they decided maybe we can do them in a CubeSat. And in fact, that became GeneSat, which was the first CubeSat launch in the United States. And it flew in an Air Force mission. But that was kind of the spark that got things going in the United States.
And now you have a partnership with NASA?
Yep.
Through the CubeSat initiative, through the Alana program?
Yep, that was kind of the next step. We did a few NASA missions, and then the Kennedy Center folks decided that this was an interesting educational program. It's basically a way for NASA to sponsor launches for a large number of universities on NASA flights. Right. And we've put a number of CubeSats in orbit from a number of universities in the United States, and the waiting list is really long, and the launches keep coming. So it's a great partnership for education.
Now, you've flown several CubeSats already in space, and this is an example of...
Yeah, this is a model of CP6.
Now, take us through the process from start to finish. How do you get started?
Most of the time we'll have a sponsor that has a mission requirement.
Okay.
So somebody, in this spacecraft in particular, we had a company that wanted to fly a component. So what the team does is at that point, we go into a design process where we start first seeing if we can do it. Okay. Can this be done on a CubeSat? And then designing what that CubeSat will look like. Our students are very hands-on. Our motto is learn by doing. So we try to do as much of the satellite as possible. So we'll design the electronics, we'll design the software, we'll design the structure. And then we go into this intense process of prototyping and testing and making sure everything works. It never works at the first time. Right. And eventually we come up with a system that we like, that we feel is reliable. Mm-hmm. And then we go into what we call flight hardware development. And we're starting to build things that have to be at flight level quality. And at that point, we put that satellite together, we put it through environmental testing, and then it goes to fly. And NASA is a great example. We'll apply for a launch with Alana, mm-hmm. We'll get a date, and then we start setting up a schedule to have a flight satellite ready for that time.
And also by working with NASA, I mean, your students are getting good hands-on experience in what it's like to go through a lot of the paperwork, a lot of the reviews, preliminary design reviews, critical design reviews.
NASA has done an amazing job at putting the students through that very rigorous quality process. NASA is extremely helpful. They understand this is a student group that's doing this work, but they don't give them any slack. Right. At the same time, they have to get to that level of quality, right. But they're there to help. And that's a really helpful and powerful incentive for the students. They're not doing paperwork right. because I tell them. They're doing paperwork because NASA is telling them, and that really has a different tone.
Now they have that experience. It's on their resume. They built a satellite.
Yep, they did build a satellite, and the students will take one of the prototypes to their interviews and say, this is what I did when I was in school. And he did a very powerful statement. Not only are our students getting value at it, but because of the large number of universities that are now able to do this, the country is getting value at it. The quality of the students coming out of universities has gone up so much that I was told by industry, somebody that interviews a lot of students, right. that for him it's almost a requirement. If you want to work for my company building satellites, I want you to have built a satellite in school. And it's also beyond the space industry. We have students that work for computer companies. They go work on phones or work on biomedical companies. Right. But the systems integration and the hands-on experience that they receive is valuable everywhere. So it's a very powerful educational multiplier, if you want to call it that.
So Brian, here at Cal Poly, you became a manager as an undergrad student in the CubeSat program. Tell me a little bit about it.
I started back in my sophomore year. I worked for about a year and a half. I ended up falling naturally into the role of just trying to coordinate and trying to keep people moving in the correct direction. Then I started working up, and eventually I filled the role of trying to manage everyone in the lab.
You said trying.
Trying. Sometimes they don't listen. It's like herding cats sometimes, but right. That's half the fun. It's a learning experience, and that's something we'll always have to remember is I'm not a dictator. People want to be here, so I don't threaten things. I don't say I get my way and stomp my feet. It's a collaborative process between everyone, and I just happen to be filling one role.
It seems like you have a really passionate group of students that work with you. You know, they have their classes, but they pile into your CubeSat lab like we're getting paid for it, and they are so into their work. So I kind of see the passion that's in them.
They see the passion a lot from the older students, the ones that have been here a long time. Mm-hmm. We used to take about 9 months to educate the people when they first came into the lab. They felt like they'd just sit there and do nothing, and they'd say, why do I need to be here? And that's the same mentality that happens when you're in a class, when you're just sitting there going, why do I need to learn algebra? And you say, this has no application to the real world. Well, when you have someone actually show you right off the bat, that actually gets them excited. When we put in the effort to just give them a little bit of a taste, they get hungry. They love to come back for more knowledge, learning, and that's ultimately what engineering is about, is that continual search for accomplishing bigger and greater things.
How many CubeSats have you worked on that are actually have flown?
So I have 2 CubeSats in orbit right now. One is CP5, which is a deorbiting sail. I came in about midway through the project, helped troubleshoot a lot of the CNDH and the radio problems that were plaguing our previous satellites. I also worked with USC on Aeneas, which is a larger satellite and much more complicated, and I worked primarily on their 2.4 gigahertz radio communications.
So when you see a larger satellite, it's not just 1 cube, it's 2 cubes or 3 cubes?
So this was actually a 3U, so large from my perspective.
Okay. Most of the cubes that you work here on at Cal Poly are we call it 1U?
Yeah, so they're just basis of units.
Okay.
So the first standard, pretty much the smallest you can go, 1Us. And we try to show what we can do with a 1U. Many other universities try to get up and run with a 3U. That's really tough. You can get into a lot of problems trying to develop full 3-axis attitude determination and control systems with deployables. A lot of people will have one thing fail and their entire system fails. And that leads to a lot of problems. We went through a much more iterative process. We're okay with launching smaller satellites because we learn so much more from having our satellites in orbit, not just continuing to work on them in development hell.
Tell me a little bit about the launch integration part of the CubeSat program here at Cal Poly.
So I'm not quite as involved. So I see it from a somewhat inside, somewhat outside perspective. It's an incredibly exciting experience. We have NASA engineers coming on campus, working directly with the students, hanging out with the students, going out and getting food with them, but also working and teaching them some of the steps in the process, because usually you're insulated at universities. So you get to see these NASA engineers that come in and say, hey, this is how we work on it in our industry, and some of which we try to copy, we try to use their vast knowledge, and sometimes we say, you know what, we're not going to be quite as thorough because it's going to get in the way of some of the really advanced development. We're just not ready for that yet.
You've actually mirrored some of the stuff that NASA's done, like in your clean room. Because when the NASA engineers come in, they're actually side by side with you guys in the clean room.
Yeah, so most teams will integrate into the P-pod, the deployment mechanism. We will do the same. We just have to walk it over. Other teams will have to ship it over, or they'll come over themselves. But every team will meet up with our CubeSat team, the launch integration side. They'll meet NASA. They'll go through the steps. Have you met all of the specifications necessary? They will all suit up. They'll go in the clean room, make sure everything's wiped down, and then they will be the last people to touch their satellite when they integrate it into the P-pod. It's an amazing experience, and you go from the very beginning concepts to being pretty much the last person that ever touches it, which is amazing, and you don't get anywhere else.
Hello, I'm Blair, President and CEO of CubeSat Industries, and I'm here to propose a CubeSat. Hello.
Hey, man. What's going on?
Hey, not much. Hey,
What are you
guys.
doing here?
Actually, I'm getting ready for my big CubeSat Elena presentation.
I didn't see that on the schedule.
You will see it this afternoon.
Okay. Well, we were on our way back to the studios, and since we stopped by, we wish you luck with it.
I appreciate that, because a lot went into this presentation. I mean, I actually went out and did a lot of research, talked to a lot of people, got good designs, I followed all the rules. I'm going to go out there and make an amazing presentation. And if successful, NASA Edge, probably within a month, will be flying their very own satellite.
All right.
Go out there and break a leg.
Yeah.
Yes, I'll do that. All right.
All right, bye.
Thanks, guys. Star, smile, strong.
What do you think?
You'll never make it.
Hello, my name is Blair. I'm the co-host for NASA Edge and the CEO of CubeSat Industries, and I'm here to propose a satellite for your consideration for the Elena program.
Oh, should be Alana program.
The Elena program.
Thank you.
Have you ever found yourself using your GPS or using your cell phone and sometimes getting sketchy data on your GPS or a poor signal on your cell phone and wondered, wow, am I using this wrong, or am I in the smack dab in the middle of a solar event? Well, now you don't have to worry. With the satellite I'm proposing, you will get direct contact from a satellite to determine whether or not your poor performance of a GPS or cell phone is user-related or solar storm related. Here we have Magnetostar 1. When deployed, the communications array opens up, deploys so that a signal can be perpetually sent to your cell phone, indicating that there's no magnetosference at all taking place. If there was a solar event and this is taken out of commission, you will no longer receive the signal, and you will know that even though I'm lost, it's okay, because it's not really my error. It's really the result of some solar activity up in the magnetosphere. So, who out there wants to add MagnetoStar 1 to their portfolio for Alana?
I guess I have some concerns. We have requirements for CubeSats. They have to meet a certain size and weight, and that looks bigger than what a CubeSat should be.
Well, actually, I'm glad you brought that up because this is scaled for demonstration.
Have you had an external group that's looked at that to say, yeah, this is meritorious and it's something that's going to be useful?
By external, do you mean like apart from family?
And Blair, how about the science? Is the science tied to NASA's strategic goals for heliophysics?
I'm in constant communication with the heliophysics group, but I haven't actually gotten feedback. It's not a loop yet. It's a one-way communication.
So if you go and look at some of the strategic goals that NASA's science goals put out, you might see where there have open questions that they want to have answered.
Oh.
And then that could help you frame your science questions better for your mission.
But don't we already have spacecraft on orbit that measures that solar event for us?
Yes, we do.
So why do we want to go ahead and put up another spacecraft if it doesn't have does it have educational benefit, Diane?
Well, that's the question I was going to ask you, Blair. As you said, this is the Alana program, and the first E is education. One of the important aspects of that is the student involvement and how are students a part of this.
I've asked some students if they'd be interested in working on it. They have some pretty strict requirements, actually, that I haven't been able to meet.
One of the things that's important for NASA is that development of the next generation workforce. So we're looking at something that helps them gain the skills that would allow them to work with and for NASA, whether it's as civil servants, whether it's with contractors, whether it's scientists, out at the universities.
So you're suggesting getting them to actually participate in building and actually making sure that MagnetoStar 1 actually functions properly.
Absolutely.
Yeah. I would love that, actually.
Is there any new design or new technology that you plan on testing as part of your BlairSat?
It's really all new to me.
Another thing, Blair, that we also consider when we evaluate proposals is schedule. When will your flight article be ready to fly, because that determines if there's a launch available if you get selected, and also your funding profile. Are you completely funded to go forward and create this satellite to completeness?
I'm willing to receive funding, yes.
Well, Blair, I think it's really ingenious on your part that you've gone from a design to a basic idea of a prototype.
I mean, this is. I mean, look at it. It went from here to here like that. I mean, I was in the workshop in my garage putting this together, and how often do you get this? I mean, not very often. It takes real creativity and ingenuity to get this far. So I believe with student help, I can get some funding and the commitments and maybe get this thing launched, which would be very important for Alana. Alana, yes. Wow, that was awesome. I can't imagine the presentation going any better than that. You could tell they loved my CubeSat. It looks like the sky's the limit here. It's about time to move to mass production. It looks like NASA Edge is finally on the map, and I'm finally going to get the respect in the scientific community I deserve.